Okay, so we are going to be transitioning from electrostatics into, so electrostatics being all the problems we were doing with all the things, electric forces, electric fields, Gauss, flux, all of those things were looking at charges that were staying stationary primarily. So there were a couple problems where we, maybe looked at how an electron, like a single electron, moved in a field. But for the most part, we were just looking at stationary charges. So if I have a configuration of charges, what kind of forces do they produce? What kind of a field do they produce? How can I use the electric field to find charge enclosed, and so on and so forth. So what we're doing is we're transitioning from that world of charges staying stationary into moving charge. And moving charge is what we call current, and that's what we use to build circuits and anything with electricity that you are using technologically in your life would be with moving charge. So there's kind of this in-between unit. So unit 1 is electrostatics, and this unit 3 that we're getting to, and it will be here soon because this middle one's short, is circuits and studies of current. But there's sort of this in-between. So how do we get charge moving? That's what we're getting into. And when we are talking about getting charge moving, we have to discuss something called electric potential. So that's what this chapter is all about. It's about electric potential. And so it is a little bit abstract. Hopefully we'll be a little bit more comfortable than what we have been doing, but still a little bit difficult to picture. And so if we are going to talk about electric potential, I'm actually going to go back in time, and we will compare that to a type of potential energy that hopefully is very comfortable for us, and that is gravitational potential energy. So if I have a cliff or something, here's a cliff, here's the ground, and the cliff has a height of h, and I have two rocks. I'm going to have a rock of little m, and I'm going to have a big rock of, let's say, 3m. And both of these rocks, of course, if I take them off of the edge of this cliff and I drop them, they will begin to fall, right? They're going to both move down. And so we would say that both of these rocks possess some gravitational potential energy with respect to the Earth. So it's the Earth rock system that produces that potential energy. And we know that that gravitational potential energy, we call it U, is equal to mgh, right? So in this case, the rock with a larger mass is going to contain more of this gravitational potential energy than the rock with smaller mass. And or if I were to change the h, that's another factor by which I could increase or decrease, if I lowered it, the gravitational potential energy of the system. So if I look at this picture, hopefully you're comfortable saying, okay, this rock has more potential energy than this rock. Or if I doubled the height, hopefully you'd be comfortable saying, okay, I doubled the height, so I've doubled my potential energy. And then we can use that energy to describe how the rocks would move. Now, for the record, they do both hit with the same velocity equal, because the mass ends up canceling out with the potential energy. It's really just a review of what we've learned already. But I did want to clarify that point. Okay, so again, I could use this potential energy to describe the direction the rocks will move. Again, it's gravity. We have an intuitive sense. There's only one direction they can move, down, right? But this is coming from this potential energy. So it's a way to describe that. So we can do the same thing with electricity. It's just that electricity is a little bit less intuitive for us. So sometimes harder to picture. So if I have two charged plates, so let's say I have a plate that is positively charged, and I'm going to call this plate A, and then I have a plate some distance away that is negatively charged, and I can call this plate B. And for what it's worth, the electric field, we'll call it E, would be directed to the right, right? If I took a positive charge and I placed it up against this wall, so this is my positive charge right here, we'll call it Q, and I placed it up against the positively charged plate.
The moment I let go, again, it's hard to picture because how can you grab a charge? You can't. But let's say I took a positive charge and I held it in some way against this wall, and then I let go. As soon as I let go, this positive charge is immediately going to begin to move. And it's going to move towards this wall over here. Because we know that these positive charges are repelling each other. In the meantime, this negatively charged wall is attracting this thing. And so it just wants to zoom to the right as soon as I let it go. And so we could say that this charged particle has some potential energy with respect to this system. So it has the potential to move when I have it over here up against the positive charge wall. And when I let it go, it's going to move over here where it will lose all of that potential. That potential energy is going to convert into kinetic energy. And by the time it gets here, it's going to have a potential of 0. In the same way that when the rocks fall and hit the ground, they've lost all of their potential for motion, right? So it's all been turned into kinetic energy. And down here, they have a potential energy of 0 because H is 0. So the same thing would happen here. If I took a charge that was twice as big, as twice as charged, let's say, so 2Q, it has more potential energy than this thing because there's more of a repulsive force just because the charges are bigger, right? So the potential energy depends on the magnitude of the charges you're placing into a field. It also would depend on the strength of the field itself, like what is the charge on this wall here and what is the charge on this wall here. So we can describe electric potential energy in the same, not the same way, but a similar way that we describe gravitational potential energy. Now, there are two terms that we use when we're talking about electricity and when I'm using the word potential. There's electric potential energy. And when I'm talking about potential energy, I will continue to use the variable U to describe it. And actually at the very end of the chapter, I'll give you an equation for this. We're not going to use it as a separate equation yet. So there's electric potential energy, and that is U, and that's going to be measured in joules, just in the same way all other potential energies are, right? Energy's unit is joules. But there's this other thing, and this is what I keep talking about. There's this thing called electric potential. So electric potential energy and electric potential are two different things. They are very, very similar. So they're directly related to each other. If something has a lot of electric potential energy, it also has a lot of electric potential, and vice versa. But they are not exactly the same. So electric potential is actually, and this is the part that's a little bit abstract. I don't think it's going to make sense why until we get much further into like the world of circuits. But electric potential, just believe me for now, is described, or it's just defined as the electric, so V is potential, as the electric potential energy per unit charge. Per charge that like depends on your situation. A lot of times we're using electrons here. And so units wise, this is the joule per coulomb. And this is used so much, electric potential is used so much that we have a new unit, which is a joule per coulomb, and it's actually named after the man who studied this. His last name was Volta, and we shorten it to volt. And I'm sure, I don't think, this is a unit that in some way you have heard before, right? That's when I say electricity, I would guess that the two units that come to mind are volts and amps. Right, and so volts are how we measure this electric potential. So when we come back to this original setup here where I have my two walls with charge, both these charges, both of these positive charges have a great deal of electric potential energy that I could calculate in joules depending on what my numbers were. They also have a great deal of electric potential. So again, just slightly different quantities, but they're directly related. So if I have a large amount of one, I also clearly have a large amount of the other, and vice versa. Let me think what else I want to say before I erase my picture. so I'm describing this all in terms of a positive charge. If I have a negative charge and place it here, it would of course have a high amount of potential over on this wall and go to 0 here. So it's going to always act in reverse, right? Because we know that the negatives repel each other and the positive and negative attract. So the negative will go against the electric field lines. The other thing is that we often talk about changes in potential because of how a battery is designed in our future. But if I have a particle or an object moving from A to B, in the same way I might have a mass moving from some height to 0, there's a change in potential and in potential energy that occur between these two plates. And so if I said, like if I refer to a change in potential, let's talk electric potential, so delta V, if an object goes from plate A to plate B, so this is where it starts, and then of course as soon as I let it go, it's going to zing over here, and this is where it ends. Delta V would be equal to VB, we like the final, VB minus VA. So the final potential minus the initial potential. So my potential when I'm at B minus my potential when I'm at A. So when I'm talking change in potential, it's just referring to change in position. We will see it as I get into practice problems in the future PowerPoints. Now, there are 4 uses for potential listed in your textbook and listed in the PowerPoint. And I just want to quickly run through those 4. We'll do practice problems with them. The 4th one really is not one we're going to practice with. I'll just show you that it's possible, but I'll gloss over it. And if you go to the textbook or follow along in the PowerPoint, when you're reading about electric potential, it can appear like there's equations all over the place. It's just a lot of equations. And so what I want to do is just hone in on, there's really just 2, okay? So 1 is the one I already gave you. Electric potential is equal to electric potential energy over Q. This is often rewritten as U is equal to Q times V. Clearly, though, these 2 things are interchangeable. They are the same equation, right? Just a rearrangement. And then the other equation that we use, and we can build all of our other problems or our other equations from this, is we're going to think about the relationship between work and energy. So this is also a review of stuff that we learned in mechanics. When we're working with electricity, we're going to assume that there's no friction. So it's all conservative forces, if that rings a bell, which means that work is equal to the change in kinetic energy. That's always true. This is the work energy theorem. Work is equal to the change in kinetic energy, and if there's no friction, the change in kinetic energy is equal to the negative change in potential energy, right? Whatever I gain in kinetic, I've lost in potential, and vice versa. And so from these 2 things, I can mathematically figure out the 4 scenarios that we problem solve with. So again, we're not gonna do the problems yet, but I just want to sort of introduce them so we can talk through it tomorrow. So these 4, let me make sure I do them in the order that you have on your notes. The first one is being able to find change in electric potential. So some problems just ask us to find change in electric potential, which is our change in voltage. And so the change in electric potential is equal to the change in electric energy over Q, electric potential energy. Or if I were asked to find the change in electric potential energy and I knew delta V, again, it's just this relationship here, okay? So if one changes, the other changes similarly. The second thing I could do is find the work done by the electric force. Assuming that there are no other forces, like there's not going to be friction or some other external applied force, we know that work is equal to the change in electric potential energy, negative delta U, which would be equal to negative Q delta V. Now this is just coming from this thing, right? That's all it is. So if I knew, for instance, that something was moving across a voltage difference, you'll hear that phrase, voltage difference, of 100 volts, and if I knew what it was, like an electron, I could find the work done on that electron. Just plug and chug. The third thing we can do is we can use the conservation of energy. So some problems, again, we'll practice with it later, but some problems might say, like, you know, how fast is something going after? So for instance, in my thing I just hit up, if I have, you know, my positive plate here, my negative plate here, and if I'd given you values for this, so like you knew voltage here and here, and I said I put a proton here, how fast is it moving when it gets to this negative plate? Well, you could use the conservation of energy. We know that our change in kinetic energy is going to be equal to our negative change in potential. So my change in kinetic energy would be negative Q delta V. And we know, again, kinetic energy is 1/2 mv squared. If we know what we're dealing with, like an electron, we can put numbers in and solve. So that's another way we can use electric potentials. And then the fourth way I'm putting an asterisk on, because we are not going to practice or use this one, it's a little bit more of a stretch. So in future college courses you might, and that is to find the work done by another applied force. So something other than the work done by the electric force. This assumes there is another external force. So we know that work, again, if this part doesn't make sense, I'm okay. Work is equal to the change in kinetic energy. If there's another applied force, this would be equal to the negative change in potential plus the work done by that other applied force. So kind of like the conservation of energy with friction, it's kind of like those problems. And then you could use that to find this if I'd given you all this other information. This one, again, a little bit less useful. So when we're solving these problems, which will be in the next PowerPoint, or the next YouTube video, sorry, and you start to see equations come up all over the place, please remember they're all coming from this very basic definition and this. That's it. This is a review of mechanics. This is real simple. Fortunately, when we're talking about work and energy, we're all in scalar quantities, so we are not going to be dealing with difficult or long mathematics here. We are not going to deal with angles. You do have to watch direction a little bit, positive and negative charges, you have to put that in correctly, but otherwise they're very, very simple to calculate with, okay? So we will stop here. Tomorrow or today, depends when you're watching this, when I see you in class, we're going to discuss briefly equipotentials together, and then you'll be using some of these concepts when you start to work on a lab with electric potential.